let's get started. So yeah, I'm probably gonna not do as much talking as I usually do, just because of my throat, right? Like I said, I have strep throat, so my voice isn't great. If you can't hear me, let me know. I can say something again or whatever. It's my understanding, at least from the doctors that I spoke to, that strep throat is contagious, but it's only contagious with like water droplets. So like if I were to like spit or like cough on you or something, the mask will stop that. So I don't think there's any risk, which is why I'm here. But yeah, I mean, if you don't feel comfortable being here, send me, like, let me know. And I don't really care if you leave. I'll give you attendance because you're here. You showed up at least. But yeah, just like let me know if you don't feel comfortable. Yeah. It's always hard to know after COVID, right? Because some people are, more cautious, and some people are more, I guess, less cautious, right? It's hard to know what to do. But anyways, if you don't feel comfortable, let me know. And I'll still give you credit. I'm not going to penalize you for that.
I think if there's any week they don't want to get sick, it's this one.
Sorry?
I think if there's any week they don't want to get sick, it's this one.
Yeah, you've got midterms next week. I get it. But yeah, it's up to you to make that judgment. Okay, so let's talk about a few different things this week. So we're going to talk about linear independence, and we're going to talk about span. Two concepts fairly closely related. Both of them have to do with sets. So both of them are talking about like a set of things or collection of things. So we say that a set of vectors is linearly independent. If I can, maybe it's actually easier for me to say what linear dependence is. So linear dependence.
Nothing can change.
Sorry?
Nothing can change.
Sure, that's fine. What's your name?
Daniel Leo.
Got it. Okay, so a set of vectors is linearly dependent if you can write one of those vectors as a linear combination of the others. Does anyone know what I mean by a linear combination? Yeah.
Like if you take all the other vectors, multiply them by individual scalars and add them together.
Yeah, right? So usually the way I'll write it is alpha 1 v1 plus alpha 2 v2 plus alpha n vn. Yeah, so those alphas are numbers, those v's are your vectors. Yeah, yep.
Things are hard to see.
Oh, thank you. I'll try turning on a light. I think that'll should help. Is that better? Okay. Yeah, it's the glare sometimes does that. So, so if we can find some alphas here so that this works, then we're good, right? We have, we're not good, it's linearly dependent. Usually that's a bad thing. You could sort of say that this vector depends on these vectors because you can write it in terms of those other vectors. But that might not be possible. So like as an example, if I gave you the vector 1, 0, and I gave you the vector 0, 1, these two are linearly independent, right? Because like I can't write this in terms of this. Like there's no way for me to do that, right? Or vice versa. So yeah, so this set here is linearly independent. But an example of a set that's linearly dependent might be like 1, 0 and 2, 0. Because this one's just double of this, right? Another example of a set that's linearly dependent would be if I took these two and then I had a third vector, 1, 1, right? Because that's just this plus this, right? So if there's a way that I can write one of them in terms of any of the others, then it's linearly dependent. Otherwise, it's linearly independent. Now, there's a notion of, there's like a sort of easier way to go about this, because sometimes you might just like stare at the problem for a little bit and think, well, I don't know if there's an actual way for me to come up with, or I guess to show that it's linearly dependent, right? Like you're looking at all these vectors and saying, is there a way that I can write one of them in terms of the others? Maybe that's hard to do. It usually is kind of hard to do, especially if there's like big vectors and there's a lot of them. So what we do is we sort of formalize this. So do you agree that I could write this here as alpha I vi equals alpha 1 v1 plus alpha 2 v2 plus all the way to alpha n vn, where this, maybe in this case, this alpha I is just 1. You good with that? I'm just saying, I'm kind of making it a little more obscure, right? But really, these two lines are the same as long as alpha I is 1, right? So, or maybe I'll say, trying to think of a good way to do this. Sure, we'll say it's 1. I can bring that alpha I to the other side, and I'm sort of obscuring some detail here, but inside these dots is going to be that alpha I vi. I'm just including it in there. Just brought it over to the other side, and that'll equal 0, right? So I guess from here, you have a system of equations, right? This is the 0 vector, because we're working in vectors, and these are vectors here. So you have a system of equations. You have the 0 vector equals, and then this bit here is actually the same thing as v1 being the columns of the first, maybe I'll write it. This v1 is the column. You take the vector v1, put it in like the column, the first column of the matrix, and then you take the vector v2 and put it in the second column of the matrix, and so on, all the way to vn. So you just take those vectors and put them in as the columns. That would form a matrix. And if you multiply that matrix by alpha 1, alpha 2, all the way up to alpha n, those alphas are just like, I mean, almost variables in a sense, right? Those vectors would be given, and those alphas are just variables. We can sort of write this, maybe we call this matrix here A, and maybe we call this vector x. Then we have ax equals 0, right? And this was one of your equations from the equivalence theorem, right? So I think you might remember that there was a property in that equivalence theorem that had this, and it said has only the trivial solution. That was like one of the points. I think it was like B or something. And then I think like maybe it was E, was that the determinant of A is not 0. So this system's always going to have the trivial solution, right? Because you could just set alpha 1 is 0, alpha 2 is 0, all the way up alpha n is 0. And that'll work. But we want to find a case where like alpha I is not 0, where maybe it's 1. And in that case, you could write one of them as a linear combination of the others, right? So if this system has only the trivial solution, then that means that you can't write one vector in terms of the others, which means that it's linearly independent. You see that? Whereas if the determinant of A is 0, this is your matrix A, determinant of A is 0, then that means that there is another solution other than just the trivial solution. So you can write a linear combination. We don't know what it is, but you can write it, which means that it's linearly dependent. Do you see that? Any questions about that? So a quick test for linear dependence is write out your matrix A and take its determinant. If its determinant is 0, then it's linearly dependent. If its determinant is not 0, then it is independent. Does that make sense? You don't even have to worry about what those alphas are. All you care about is this matrix, which has the v's as the columns. The vectors are given as the columns. Hopefully that makes sense. So then span is another concept. Actually, I think I want to talk a little bit more about independence, sorry, before I move on. Let's think about let's think about independence in a bit of a different way. And I think this is something you haven't seen before, and I really try to focus on this for this lecture, or for this part. So say that you have a set of vectors that just has one thing in it. Maybe it's just like V1, right? Is that set linearly dependent or linearly independent? Just has one thing in it. Independent, right? Just like there's only one thing. It can't depend on anything else in the set. There's only one thing, right? So yeah, this is linearly independent. It's always going to be linearly independent. There's actually one exception, but we're going to leave that for now. If I add a second vector, is it linearly independent, linearly dependent, or you can't tell? Need more info. Need more info, right? Maybe it is, we can sort of think of it like visually, right? So if this was V1, maybe V2 goes right on top of it, in which case it's linearly dependent, right? Or maybe the second vector goes like in a different direction. Maybe that's your V2. So we don't know. But there is one thing that we do know, which is that as you keep adding vectors, eventually you're going to hit a point where any vector that you can come up with that you could add to that set is always going to make it dependent. So there's sort of like a maximum, right? Sort of like you can keep adding vectors and adding vectors until like eventually you hit like a maximum number of vectors that you could have in a set so that it's still independent. And if you add any vector to it, it's going to become dependent. You sort of see that? So like if we were working in like R2, which maybe it's just the plane of this whiteboard, if I draw one vector, that's fine. If I draw a second vector, that's fine. But keeping my vectors on this whiteboard, there's no vector I could draw, right? That I could add to this set that would make it independent still. It would lose that independence, no matter what vector I add. If I add one here, then maybe it'll be like some scalar multiple of this and some scalar multiple of this, like negatives, right? Either way, you can build up any possible vector that you could come up with in R2 using those two vectors, right? So it's kind of a max. And this happens at like a magic number of vectors. So it's like a specific number of vectors. So let's talk about span. So span, this one often confuses people. The span of a set of vectors, say v1 through vn, it's a function. It takes in a set of vectors, keyword there is a set of them, and it outputs a set of vectors. So it takes in a set and it spits out a set. The set that it spits out is all the possible linear combinations. So it spits out the set of every possible thing you could reach using those vectors. That's how I like to think of it, is like, what stuff could you reach, right? So like, as an example, if I have this vector as my v1, and I have this vector as my v2, I can reach like this vector, right? By using like some number of these v1s and then some number of the v2s, I could reach it, right? So this vector here, this long one, is in this span of these two v1 and v2. Maybe I call this like, I don't know, w. I would say w is in the span of v1 and v2, because I could reach it using v1 and v2. Does that make sense? But if I were to have, like, as an example, like this vector sticking out of the page, I couldn't reach it no matter what I did with v1 and v2, right? Like, there's no way I can get off the page just using those v1s and v2s. It's always going to be on the page. So that means that this vector that sticks out of the page, that's not in the span, right? But I could maybe add that vector to this set, so that maybe this is v3, then I could have a span of v1, v2, and v3. And that would make my spanning set larger, right? It would reach more things, because they could now come off the page. But again, there's almost a diminishing return, right? Because after a certain point here, if you keep adding stuff to the span, it's not going to change what it can reach, right? So if we were only working in R2, if I added another vector v3 in R2, it's not going to change what it can reach. It can still reach everything in R2. If I had a fourth vector, it's not going to change what it can reach. It can still reach everything in R2. It already could, right? So there's like a magic number of vectors. Now the neat thing here is that that magic number of vectors and this magic number of vectors is the same. It's called the dimension of the vector space, or of the vector space. So that's something I don't know if you've learned that yet, but you will pretty soon. Any questions? Does that make sense? Show of hands, who feels good with linear independence? Who feels good with span? Okay. Maybe some practice will help, I think.